A single laptop just went head-to-head with a 5,000-qubit quantum computer and matched it. Not approximated. Matched. The kind of result that isn't supposed to be possible, according to a peer-reviewed paper published in one of the most respected scientific journals on Earth. Before we go any further, there's something you deserve to know up front, because this story has been circulating online with a detail that simply isn't true. The company involved wasn't Google, and the researcher who led this work isn't 22 years old. Read that again, because getting this right actually makes the real story better, not worse. What actually happened is stranger, more contested, and more consequential than the version making the rounds, and it sits at the exact center of a technology race that genuinely could decide who leads the next decade of computing. Let's start by correcting the record, because an honest telling of this story matters more than a catchy but inaccurate headline. The company whose quantum supremacy claim came under fire wasn't Google. It was D-Wave, a Canadian quantum computing company that, back in March of 2025, published a peer-reviewed paper in the journal Science, announcing something genuinely remarkable at the time. Using its Advantage 2 processor, it's a quantum annealing machine packing more than 5,000 qubits, D-Wave claimed to have achieved the first demonstration of quantum computational supremacy on a real, useful, practical problem. Not some artificial benchmark engineered purely to be hard for classical computers, but a genuine simulation of how disordered magnetic materials behave at the quantum level, the kind of physics research that actually matters to scientists working on next-generation electronics, sensors, and superconductors. This is not chaos. This is precisely the kind of headline-grabbing announcement that had been circulating throughout the quantum computing industry for years, one company after another claiming to have crossed a line no classical computer could ever follow them across. And the researcher who eventually challenged that specific claim isn't a 22-year-old prodigy either, though the truth about who he actually is, arguably, makes the story more compelling, not less. His name is Joseph Tyndall, and he's an associate research scientist at the Flatiron Institute's Center for Computational Quantum Physics in New York, part of the Simons Foundation. Tyndall holds a doctorate from the University of Oxford and a master's degree from the University of Bath, and before joining the Flatiron Institute in 2022, he'd already spent years working as a postdoctoral researcher, including a stint applying quantum mechanics inside the business world at a company called Quantum Dice. Think about what that background actually represents. Not a lone genius stumbling onto a breakthrough by accident, but a genuinely experienced, formally trained physicist, backed by years of specialized research into exactly the kind of mathematics his eventual challenge would depend on. Working alongside 4 collaborators, Antonio Francesco Mello, Matthew Fishman, E. Miles Staudenmeier, and Dries Sells, spanning the Flatiron Institute and Boston University, Tyndall's team published their own paper in Science in May of 2026, and what they demonstrated inside it genuinely does read like something out of an underdog story, even if the underdog himself isn't a college sophomore working out of his dorm room. Here's the detail that made this story spread so quickly across the scientific community and beyond. And it's a genuinely true, genuinely remarkable detail, even without exaggerating anyone's age. Joseph Tyndall ran many of his team's earliest calculations, the ones that would eventually challenge a 5,000-qubit quantum computer's headline result on a personal laptop. Not a supercomputer cluster, not a specialized research facility humming with racks of dedicated hardware. A laptop, using a piece of open-source software called iTensor, a tensor network library the Flatiron team itself had been developing for years. Read that again, because the sheer scale mismatch is exactly what makes this story worth telling honestly, rather than needing to inflate it with a fictional 22-year-old. A machine built from over 5,000 delicate, individually cooled quantum bits, cutting-edge hardware representing years of specialized engineering and enormous capital investment, found its headline result matched by mathematics run on consumer-grade hardware sitting on someone's desk. The specific technique behind this achievement deserves genuine explanation, because it reveals something important about how this entire field of classical versus quantum competition actually works underneath the headlines. Tyndall's team used something called tensor networks, a mathematical method for compressing the description of an incredibly complex quantum system down into a form small and manageable enough for ordinary computer hardware to actually process. Think of it like an extraordinarily sophisticated form of data compression, one that manages to capture the essential physics of a system without needing to track every single possible quantum state it could theoretically occupy, most of which turn out to be largely irrelevant to the final answer anyway. But tensor networks alone weren't quite enough to match D-Wave's specific result. The genuinely clever part of Tyndall's approach involved combining that tensor network method with something called belief propagation, a mathematical routing technique that, remarkably, dates all the way back to 1982, originally developed for an entirely different purpose and left largely dormant for decades, before this team revived and repurposed it for exactly this problem. Miles Staudenmeier, one of Tyndall's co-authors, described the resulting method's specific trade-offs with refreshing honesty. It's a little more approximate than some of the other methods, he explained, but it's way cheaper, and we can run it much more directly on lots of harder problems. Think about what that admission actually reveals. This wasn't a method claiming perfect, flawless precision. It was a method trading a small amount of accuracy for an enormous amount of computational efficiency. And that trade-off turned out to be exactly what was needed to match D-Wave's specific published result. Now, here's where an honest telling of this story has to slow down and resist the temptation to declare a clean, simple winner. Because what actually happened next reveals something genuinely important about how real scientific disputes unfold. Messier and more contested than either a triumphant headline or a quiet retraction. D-Wave didn't simply accept defeat. The company issued a detailed, technically substantive public response, and the language it used was direct. The claim that D-Wave's achievement has been overturned is inaccurate and not supported by the scientific record, the company stated. Read that again, because it's the exact opposite of what a simple laptop beats quantum computer headline implies. D-Wave welcomed the Flatiron team's work as a genuine, meaningful contribution to the field, but pushed back hard against the specific idea that it had definitively matched, let alone surpassed, everything D-Wave's original paper had claimed. According to D-Wave's own technical rebuttal, Tyndall's classical method hadn't actually attempted the most complex lattice geometry involved in the original research, hadn't reproduced the largest simulations run in three-dimensional configurations, hadn't tackled the specific low-precision scenarios where quantum correlations spread and propagate at their absolute fastest, and hadn't produced several of the more advanced statistical measurements D-Wave's original team had reported. This is not chaos. This is precisely how genuine, high-stakes scientific disputes actually work. Not a clean knockout blow, but a careful, technical back and forth, each side pointing to specific gaps and specific strengths in the other's methodology, playing out in public, in real time, through peer-reviewed publications and formal corporate statements rather than a single decisive headline. Understanding why this specific dispute matters enough to potentially influence something as enormous as the entire US and China quantum computing race requires zooming out and recognizing a pattern that has repeated itself, almost eerily, every single time a major quantum supremacy claim has ever been made. This isn't the first time a headline-grabbing quantum breakthrough has faced exactly this kind of classical counterattack, and understanding that history reveals just how high the stakes genuinely are. Back in 2019, Google's own Sycamore processor made global headlines with its original quantum supremacy claim, estimating that a specific calculation its quantum chip completed in about 200 seconds would take a classical supercomputer roughly 10,000 years to match. That estimate didn't survive contact with reality for very long. Within days, researchers at IBM, Google's own direct rival, published work suggesting the same calculation could actually be completed in a mere 2.5 days using improved classical techniques and sufficient disk storage. By 2022, researchers working independently had pushed classical algorithms even further, making them roughly 10 orders of magnitude faster than the methods Google had originally used for comparison. Think about what that specific historical pattern reveals and why it matters so directly to the story unfolding right now with D-Wave. Every single major quantum supremacy claim made across the entire history of this field has eventually faced a serious classical challenge. And in nearly every case, that challenge succeeded in narrowing, if not completely erasing, the gap the original claim had promised. This is precisely why one detailed 2026 industry analysis of the entire quantum supremacy landscape offered a conclusion worth repeating carefully, because it captures the genuine, honest state of this entire field better than any single headline ever could. Classical algorithms, especially tensor network methods, repeatedly narrow or erase claimed gaps, the analysis states, so every supremacy result is provisional. A demonstration that looks classically impossible one year can be matched on a cluster or even a laptop a year or two later. Read that again and notice something genuinely important buried inside that specific phrasing. This isn't describing a single isolated dispute between one classical researcher and one quantum company. It's describing an entire ongoing structural pattern running through the whole field, one where every quantum breakthrough exists under a kind of permanent probationary status, always vulnerable to being narrowed or overturned by the next clever piece of classical mathematics somebody manages to develop. Now, here's where the story genuinely does connect to the broader you. China quantum race sitting inside this video's own title, because this specific pattern of claim and counterclaim hasn't stayed confined to a single country or a single company. Quantum supremacy claims have been genuinely, actively traded back and forth between American and Chinese research teams for years now, each side pushing the claimed gap between quantum and classical computing a little wider, only to watch classical researchers push back and narrow that same gap shortly afterward. China's University of Science and Technology built its photonic Zhuzhong processor back in 2020, followed by its own superconducting Zhuchongji chips in subsequent years, each one making its own headline-grabbing claims about outperforming classical supercomputers. Google's own Willow chip pushed the American side of this competition forward significantly in 2024, and China's own Zhuchongji 3. Zero answered that specific challenge again in 2025. Think about what this back-and-forth pattern actually reveals about the true nature of this entire technological race. It isn't a single dramatic finish line either country crosses once, permanently and definitively. It's an ongoing, iterative competition, where each side's claimed lead gets tested, challenged, and sometimes narrowed by classical mathematics, only for the next hardware generation to push the gap forward again in an endless, genuinely fascinating cycle that has repeated itself for the better part of a decade now. This is exactly why classical breakthroughs like Joseph Tyndall's laptop-based challenge to D-Wave carry genuine strategic weight, regardless of which specific company or country happened to be on the receiving end of this particular result. Every time a classical algorithm manages to match or narrow a quantum computer's claimed advantage, it doesn't just embarrass one specific company, it resets, at least partially, the entire scoreboard everyone involved in this broader race is quietly keeping track of. If China's own research institutions can develop or adopt similarly clever classical techniques, tensor networks, belief propagation, or methods not yet invented, capable of matching American quantum hardware's claimed advantages, the practical lead, a specific piece of quantum hardware, provides shrinks considerably, regardless of how many qubits that hardware happens to contain. And the reverse holds true as well. If American classical researchers, working at institutions like the Flatiron Institute, keep developing techniques capable of matching or narrowing Chinese quantum claims, that becomes a genuine, meaningful form of technological leverage in its own right, one that doesn't require building a single additional qubit to matter. It's genuinely important to distinguish this specific D-Wave dispute from what's actually happening over at Google right now, because conflating the two would misrepresent where each company's own quantum claims currently stand. In October of 2025, Google's Willow chip ran an algorithm called Quantum Echoes, and according to the company's own published results in the journal Nature, that algorithm completed a specific physics task roughly 13,000 times faster than the best available classical method running on one of the world's fastest supercomputers. Here's the detail that genuinely separates this specific Google result from the more contested D-Wave situation described earlier in this video. Google's earlier 2019 Sycamore claim relied on something called random circuit sampling, a task that was, by its very design, essentially impossible to independently verify without running the exact same infeasible classical computation the whole experiment was supposedly demonstrating was impossible in the first place. Quantum echoes work differently, producing what's called a deterministic verifiable outcome, a specific measurable physical quantity that, in principle, another quantum computer entirely could independently reproduce and cross-check against Google's own reported numbers. Think about why that specific design choice matters so much, given everything else covered in this video. Google appears to have learned directly from the exact pattern of classical counterattacks that has repeatedly undermined prior supremacy claims throughout this field's entire history, deliberately designing an experiment harder to challenge, using precisely the kind of clever classical mathematics that eventually caught up with Sycamore in 2019, and that has now, at least partially, caught up with D-Wave's own 2025 claim as well. As of the most current research available, no published classical counter-demonstration has yet challenged Google's specific quantum echoes result, a genuinely important distinction worth holding on to as this broader story continues to unfold. Sundar Pichai, Google's own chief executive, has set a considerably more ambitious target for where this entire technological race is actually headed next, one that moves well beyond any single benchmark dispute, like the one currently playing out between D-Wave and the Flatiron Institute. Pichai has publicly stated a goal of building a genuinely useful, fully error-corrected quantum computer by 2029, part of a broader 6-milestone roadmap the company has laid out, ultimately aiming toward a large-scale machine capable of controlling roughly 1 million individual qubits. Think about what that specific, considerably longer timeline actually implies about everything covered earlier in this video. The entire drama surrounding whether a laptop can match a 5,000-qubit annealing processor on one particular physics simulation, however genuinely fascinating and however contested, represents just one small skirmish inside a considerably larger, considerably longer war, one where the ultimate prize isn't winning a single benchmark dispute, but building a machine reliable enough and powerful enough to solve problems no classical computer, no matter how cleverly programmed, could ever hope to match. Not through some temporary computational trick, but through a fundamental, permanent difference in underlying computational power. This is precisely why one of the most honest, carefully worded assessments of the entire quantum supremacy field published throughout 2026, deserves to close out this story rather than a simpler, more triumphant conclusion. Supremacy is not the same as useful quantum computing, the assessment states directly. Beating a supercomputer at random sampling does not factor numbers, simulate molecules, or break encryption. The real goal is useful, error-corrected quantum advantage on valuable problems, which had not been achieved as of 2026. Read that again and hold it directly against the framing suggested by this video's own original title, the idea that a single dispute, however genuinely fascinating, could single-handedly decide an entire international technological race. It can't, not by itself. What Joseph Tyndall's laptop-based challenge to D-Wave actually demonstrates, honestly and accurately, isn't a final verdict crowning either quantum or classical computing the ultimate winner of this broader competition. It's a genuine, healthy, ongoing reminder that this technological race remains fundamentally unsettled, contested at every single benchmark along the way, precisely the kind of rigorous, adversarial scientific pressure that keeps every single claim, whether it comes from D-Wave in Palo Alto, Google in Mountain View, or a research institute in Hefei, honest, verified, and genuinely earned rather than simply accepted on faith. So where does the honest, carefully researched version of this story actually leave us? Not with a 22-year-old prodigy single-handedly deciding the fate of an entire international technological race through one dramatic laptop calculation, however compelling that specific framing might sound. Instead, with something considerably more interesting once you actually understand it correctly, an experienced, formally trained physicist backed by a genuinely capable team of collaborators using decades-old mathematics revived and cleverly repurposed for an entirely new problem, matching a headline result from one of the most advanced quantum computers ever built, using nothing more exotic than a personal laptop. D-Wave has pushed back hard with specific, technical, genuinely substantive objections that remain entirely unresolved as of this recording. Google's own separate quantum claims have so far avoided this exact same fate, at least for now, having deliberately built a more verifiable, harder-to-challenge experiment, specifically to withstand precisely this kind of classical counterattack. And the broader US. China quantum race continues unfolding exactly the way it always has, not through a single decisive victory either side permanently claims, but through this same genuinely fascinating, endlessly contested rhythm of claim, challenge, and counter-challenge, playing out across peer-reviewed journals and corporate press releases on both sides of the Pacific, with no single laptop, no matter how cleverly programmed, likely to settle the entire question once and for all. If you want to understand exactly what happens once Google's own claims eventually face their own classical counter-challenge, the same pattern that is now caught up with every single major quantum supremacy claim throughout this field's entire history, or what happens if Chinese research institutions develop their own version of the exact tensor network techniques covered throughout this video. That's precisely the story we'll be tracking closely as it continues to unfold, so make sure you're subscribed before that next chapter finally arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does the genuine, ongoing pattern of classical mathematics repeatedly catching up with quantum computing's boldest claims make you more skeptical of the next dramatic quantum breakthrough headline you come across? Or does it make you more confident that this rigorous, adversarial process of challenge and counter-challenge is exactly how science is supposed to work, correcting itself in public, one contested claim at a time? Leave your honest answer down in the comments below, and as always, I read every single one.